Jai Hind everyone. I am Achintya Pandey as an assistant professor in Department of Information Technology at Ajay Kumar Garg Engineering College. Okay. So today I will discuss, this is my second video of this data structure in this session. So today's topic is stacks and queue data structures. So in my first video of data structure, I simply discuss the data structure, different kind of data structure, right? So as you know, the data structure is a mathematical and logical arrangement. Mathematical arrangement of data means how the data is going to organize. So this is particular. The stacks and queue are standard data structures, and stack is a last in first out kind of data structure, while queue is a FIFO based data structure, means first in first out data structure. Okay. So this is an organization, and you can see this is stack organization, where if you want to add some book, you can add only at one end, top end. Even if you want to remove a book, okay, then you can just take one book from top end. Means in this stack data structure, insertion and deletion, insertion and removal, okay, of element can be done at one end, and that is called top end. Okay. So while queue, there is a two end, one is front and second one is rear. So from front end you can remove the data, and from rear end you can insert new element to the queue. Okay. So what is stacks? So stack is a data structure of order item such that items can be inserted and removed only at one end, and that is supposed to be top end. Okay. So what can we do with a stack? So there are the insertion operation in stack terminology is called push operation, while the removal or deletion operation in stack terminology is called as pop operation. Okay. So push operation means this push operation place an item on the stack, look at the item on top of the stack. I mean the item at the top is called peek, but do not remove it. Pop is what? Just removal from the top end is called pop operation. Okay. So it is like said, stack is the last in LIFO data structure. Okay. It is sometimes called push down store. Okay. So these all are some application of stack: program executions, parsing, evaluating, postfix expression. Okay. There are many other applications where stacks are used, like you can use in a quick sort. Okay. And there are many other areas where you use stacks. Okay. Now the problem, what happens if you try to pop an item off the stack when the stack is empty? Okay. So there are two operations which is used in this terminology. One is underflow and second one is overflow. So these operations, underflow means say in particular stack, if it is empty and you want to remove some item, this situation is called underflow. Okay. And when stack is full, okay, say stack is of size max size and the items are filled up to the max size, and you want to insert further an item into the stack, so this situation is called overflow. So underflow and overflow are two conditions which we check, especially while removing and inserting an item. Whenever we want to say insert, first we check either there is a space or not. If there is no space and you want to insert, so the system should raise issues that this is the overflow condition. Okay. So what happens if you try to pop an item off the stack when the stack is empty? This is called underflow. The pop method needs some way of telling us that this has happened. In Java, we use this particular java.util.empty stack exception just to mark the underflow situations. Okay. So stack could be implemented by array as well as linked list. Okay. So the implementation of stack can be done from the array as well as the linked list. So implementing a stack using an array is quite easy. So the bottom of the stack is at data 0. The top of the stack is, say, if we have number item -1, because it will start from 0. Okay, so push onto the stack like this. Okay, and pop up the stack at the top element. Okay. Okay, implementing a stack using a linked list is not that bad either. Yeah, so you can simply use the linked list just to implement the stack. So store the item in the stack in a linked list. The top of the stack is the head node. The bottom of the stack is the end of the list. Push by adding the front of the list, and pop by removing the front of the list. Okay, reversing a word. We can use a stack to reverse the letter in a word. Okay, suppose if you want to find just the reverse, so you can use stack, because the last item, the last alphabet which in the word occurs will be at top, and simply remove from top, you will get the just reverse out of it. So when, okay, so how we are going to reverse? Read each letter in the word and push it onto the stack. When you reach the end of the word, simply pop the letter off of the stack and print them out. Okay, so it will, the stack will simply, reverse the string. Okay, if you want to say reverse the string, you can simply use a stack. Okay, now one very important algorithm is here, just to just if you want to convert an infix operation into postfix operation. See, stack is used for postfix evaluation. Okay, now here the algorithm is written for, if you want to convert infix operation, simple arithmetic operation, okay, into postfix. So there are three way of writing expression. One is called infix, other is called prefix, and third one is called postfix. So in infix, we write the operator between two operand. In prefix, we write the operator before two operand, and in postfix, we write the operator after the operand, after two operands. Okay, so this is the algorithm polish QP. Say infix operation is also called as a polish notation. Okay, so we have polish, reverse polish. Okay, so suppose this is the expression. Suppose Q is an arithmetic expression written in infix notation, and this algorithm polish QP means this algorithm will particularly convert the infix expression written in Q into the postfix expression P. Okay, so there are 6 steps of this algorithm. Okay, so see, just want to elaborate all these 6 steps. Okay, suppose Q is an arithmetic expression written in infix notation. This algorithm will find the equivalent postfix expression. Okay, so the first step is you say require a sentinel value, say operand. In infix, generally we can use open and close parenthesis. Okay, so first step is simply push this open parenthesis onto stack, and this add to the end of the Q. Q means the expression which we want to convert into the postfix. So we are simply using say open parenthesis. Okay, and initially we put it on the stack, and the close parenthesis we put at the end of the expression. Okay, so second is scan Q. Q is what? The expression which is written in infix. So scan Q from left to right and repeat step 3 to 6. This particular step 3 to 6. Okay, so see one by one. So any expression which is written in infix could have operand, could have operator, could have open and close parenthesis. These all are the elements which could be encountered in any infix operation. It could have open parenthesis, it could have close parenthesis, it could have operand, and it could have operand. Okay, so we will simply see what it encounters. Say, so if an operand is encountered, okay, then add it to P. P means, say, here we will use a stack, and this is the, say, converted expression P, which will be come into the, and this will be the, say, symbol which is going to scan. Okay, so we can make a table. So if an operand is encountered, it will simply append into, add it to P. Okay. Second, if a left parenthesis is encountered, push it onto stack. Here we need to put it into. If an operator is encountered, so there are two conditions. So if simply operand is encountered, we can push simply into the expression Q, which we want to find. Okay, means the postfix expression. Okay, so next, if an operand is encountered, then simply it will add into the P. If a left parenthesis is encountered, we will simply put it into the stack. If an operator is encountered, say any operator been encountered, so we will repeatedly pop from stack, and add to P each operator. Okay. Whenever an operator will be encountered, we will pop from stack and add to P each operator on the top of the stack, which has the same precedence as or higher precedence than this current operator being scanned. Okay, meaning is that if a new any operator is encountered, if there are operator which is on stack having the precedence higher or equal to this just current operator scanned, if it is, then we will simply push it onto the P. If it is not so, it will simply be there in the stack. Okay. So if it is so, after that it will add this current scan operator to the stack. And last, if a right parenthesis is encountered, then we will repeatedly pop from stack and add to P each operator on the top of a stack until a left parenthesis is encountered. And at last, we will simply remove the left parenthesis. Okay. So we have seen here that there are all conditions. I mean, either operand is encountered, a left parenthesis is encountered, or operator is encountered. So with the operator, there are two cases. If the current scanned operator is, if suppose the current scan operator is, okay. So in stack, if the operator are having greater precedence or even equal precedence to this new scanned operator, then we will simply pop from the stack and add it to P. If it is not so, it will be as such into the stack. At last, we will simply push this current new scan into the operator into the stack. So let's see this algorithm into these questions. Okay. Suppose this is the expression written into the infix mode, and now we want to convert this expression into the postfix, means Q. This is the P, and this which we want to convert into, actually this is what? P. Okay. And we want to convert into Q. Q means expression written into postfix. Okay. So we simply, numbered all the symbol which is there in infix, so that we will find how many entry will be in the table. Okay. So there is a symbol, scan, stack, and expression. Okay. So we simply put just open parenthesis into the stack, and this at last we simply put the close parenthesis into the Q. Q means P. Okay. P means expression which is written in, infix expression, infix mode. Okay. Now see one by one. So first symbol scan, first is operand A. So we will simply put it into the P. Then we have operator, we will put it on the stack. There is no operator in the stack earlier, so we will simply put it on the stack. Then we have open parenthesis, we will put onto the stack. Then we have At the fourth element is simply operand. We'll put into the expression P. Then we have operator. Now this is the current scan operator, say asterisk multiplication, and there is no operator in the stack. Okay. So we'll simply put into the stack. Then we have again operand C. So simply we will append the C into the P. Then we have operator minus. Okay. Now in stack we have already multiplication operator asterisk, which is having higher precedence than this currently scanned minus operator. Okay. So simply we'll remove, pop from stack this particular operator, and we will put it into the expression, and this new scanned operator minus will come into the stack. Similarly, we have open parenthesis, we will put into the stack. Then we have operand D, we will put into P. Then we have again operator, so simply we will put into stack. There is no operator at top, so we will simply put in this currently new scan. Then again we have E. E means operand, put into P. Then we have exponential operator, say this one, which is having the highest priority. So we will simply put it into the stack. Now in stack we have operator division operator, which is having less precedence than this current scan operator. So it will not be removed from the stack. That is the point which is important here to note that. Okay. Then we have next F, new operand. So we'll put into here P. Then we have close parenthesis. So one close parenthesis will operand. We will simply pop the operator from stack until open parenthesis encounter. So we will simply eliminate this one. Okay. So this will come. Then we have operator multiplication, simply put down, and so on. So this expression we have encounter all the cases. So at last we will get this expression. Okay. So this is an important, there are many questions comes to convert infix into postfix. Okay. So what is the algorithm? Again, just there are two tests. We simply have a stack and simply the expression which is to be converted into postfix. So if an operand is encountered, it will simply return into the P. If an operator is encountered, it will come into stack, and we will see is there any operator which is having higher or equal precedence than this current new scanned operator. If it is show, we will simply pop from stack and add it to P, and after that we will simply put this currently new scanned operator into the stack. Okay. Then if left parenthesis comes, we'll put it in stack. If right parenthesis comes, we'll remove operand one by one till we get the left parenthesis. This is how we convert infix into the postfix. Next data structure is a queue data. Queue means first in first. Just we can see that this is a queue kind of organization. Okay, the man which come the person which come first will be served first. So that's why this queue data structure is called first in first out data structure. Okay. So queue is a data structure of order addressing such that item can be inserted only at one end and removed at the other end. Other end means if any new persons come, they will simply stand at last position. Okay, rear end. Okay, so this one is called front end, and this one is the rear end. Okay. Okay, so that's why it is FIFO data structure. Okay, a line, for example, a line at a supermarket. Okay. What can we do with a queue? So there are two operations which is called Enqueue and Dequeue. Enqueue means if you want to add an item to the queue, and Dequeue is called in queue terminology. Enqueue and Dequeue operations are used, and these operations are for insertion and removal. Okay, so adding is Enqueue and removing is Dequeue. So these operations are also called insert and get front in order to simplify things. Okay, the FIFO data structures, These all are some application of queue, round robin scheduling in processor, input output processing, queuing of packets for delivery in network. Okay, just like stack, queue could be implemented either by using array or by linked list. Okay, so all this could be done. Using array to implement queue is significantly harder than using an array to implement a stack. Okay, because to implement a stack. Okay, significantly harder using an array to implement a stack. Okay, comparatively, this queue implementation using array is little challenging than the stack. Okay, unlike a stack where we add and remove at the same end, in queue we add to one end and remove from the other end. That's why it is comparatively complex than the stack, because in a stack insertion and deletion can be done at one end. That's why implementation is more easy as comparison to stacks. Okay. Okay, so again there are two options for implementing a queue using an array: Enqueue and Dequeue. Okay, Enqueue at data 0 and Dequeue from data num item -1. Okay, Enqueue at then these are the steps just for implementing a queue. Okay, so this is implementing a queue using a linked list. It is still easy. From front of the queue is stored as the head node of the linked list. Rear of the queue is stored as the tail node. Enqueue by adding to the end of the list. Dequeue by removing from the front of the list. Okay. So this is all about stacks and queue. This is very fundamental data structure which is used in data structure which have many applications, and this is the all about the stacks and queue. Thank you very much.